We have in order, and what's the second method that we need to write? The void in order. And what's the parameter for this? Or is there any parameter? The node, that would be the copy of the root node, right? So a pointer to the root node. So in this case, we'll just call that current. And what happens in the public method? Call the private method. So all we're going to do is we're going to call the private method. And what are we passing it? The root node. So this dot. Anyone who doesn't understand, when you pass in an object just like this, it doesn't actually make a new copy of that object. It just creates a new pointer to that object. So when we're passing in this dot root, we're just making a copy of that point, right? So let's say the tree is just like this right here, and the root is pointing here. When you pass in this dot root, what this does is just makes a current pointing to the same thing. It doesn't make a copy of the whole thing, because that would be taking a lot of space. With objects in Java, it just makes a copy of the pointer. All right, so what happens inside this one? So we're going to test if current equals to null or does not equal to null. And what should we do? If it is equal to null, then we want to print that out, right? Current is equals to null, then the tree is empty. So we're going to do something like that. Remember, we're printing the whole tree in order. In order means in what order? Ascending order. And remember, there's left root, left node, the node itself, and the right node, right? So which order would that be in? So this would be like the root node, right? So we're trying to print that in this order. Left first, then the node itself, and the right. So in this case, what's the first node are we going to print? Far left, which is this one, right? So this is the left, this is the node itself, and this is the right. But when we get to here, this is the node itself, and this is the right. So every single one has a different one. So how do we call recursion, or do we do in order? And we pass in current. Where are we passing it? Dot net. And then what's next? Node current dot data. So we're just going to print that out. So we're going to do s out node current dot data, just like this. And what happens is anything happens after that? We'll do in order, and we should pass in current dot right. So now let's go and test it out. So we have two trees. We have string tree and we have new car tree. So let's see if we can do car tree dot in order. Car tree dot in order is not working. Why is it not working? We won't be able to do this in car tree class. Let's try this, because we're trying to print the data itself, but it's saying it doesn't know how to print that data's value, because remember, it's a generic. When you create it, it doesn't know what data it's going to be. Let's actually create a list and just return the list instead. And in here, we can come. So this would work if we had an int tree, not a generic type tree. So let's add a list and we can return that list. How can we add the list here? We're going to, instead of printing it out here, we're going to add everything to the list. Create an array. So we're going to create an array in a public class. And we're going to do array list. And this would be type of T. We're going to keep it generic, and then we're going to call that list, and we're going to actually initialize it equals to new array list. And how do we get this to the other function? Pass it as a parameter. So we're going to pass it as a parameter. We're going to pass it as a list here, and we're going to cast it as a parameter here. So we're going to do array list type T. That would be generic. And we're going to call that list again. Now we have the list. We're going to return the list. We need to change the void. And then every time we try to print something, we're going to, instead of printing it, we're going to add it to the list. Right? So in here, we're going to change this to array list, generic type. And after calling the function, we're going to return. Do we need a return type for this one? Or can we do it without? Remember, when you're passing in data structure, so array list is a data structure like this, right? So when you're passing that in, this is just passing the pointer down to, just creating a new pointer down to the same data structure. So if you have a list like this, it's just creating a new pointer pointing here, new pointer pointing here. Every time you call recursion, it's not, you're working with the same data structure. So even if you don't return it, you're just modifying the same one over and over again. So in this case, we don't actually need a return type. So here we do need to pass in the list, and we'll pass that in. And here, remember, instead of printing it, we can just do return. And here, we need to add it to the list. How can we add it to the list? It's simple, right? So list.add, and we're going to add current.data. Remember, the data itself is generic T class, right? So this is the generic data. We can just add that in there. That would satisfy the generic data type for array list. So now if we go back and look at generic main, that error went away, and we're going to try to print the car class and see what happens. Car tree, and we'll run this. So it's printing based off of, I think, miles per gallon. That's how the car is designed to print. I'm running the main class. I'm not running this class. My bad. All right. Let's run this now. So it returned a list of everything. Remember, it's not printing the whole tree. We're returning a list now. And it returns the list in order. Let's try the car tree now. That should work too, because we have a toString method in there. Yes. We have color and MPG in order from left to right. We have a size in there, and we're increment. Okay, so the size would be easy. Let's write a method called height. We're going to get the height of this tree. What's the height of this tree? Or let me add some values here. 10, 5, 15, and 1, this is 5, 7, that's 11, and this would be 17, right? So what's the height of this tree? 3. We start right here and go down how many levels we have, 1, 2, and 3. So that's what we're going to check. We're going to write a function that does that for us. So we have public. How would we write? It would be void. Remember, the height method is going to tell us the height, right? So it's going to return an integer, right? So it's going to return one of these 3 numbers, 1, 2, or 3. So it's going to return an integer, a value, and we're just going to call that height. And just like when we call it recursion with any other function, we need a private method with this. We need to make a copy of the root. And in this case, we're actually going to do int height. And this one is going to take in a node of current. And that would be the copy of the height. I'm sorry, copy of the node root class, root node. And how are we going to call this function from the public method? We will return height, and we're going to pass in just our root. So whatever this function is returning, we're going to return that. And how are we going to calculate that? So we're going to check if current equals to no. If that is the case, we're going to return 0. So that could be the base case, right? And then what else? In this case would be height, right? Count levels or height. So height, and we're going to pass in current.left, compare that to height current.right, like this. All right, so now I think we're missing one minor detail in this. So what we're doing is, remember, this doesn't have to be a perfect tree, right? It could be a tree that goes like this, something like this. So now the height of this tree is 1, 2, 3, 4, 5. But on this side, it's only 3, but this side is 5. So what we're doing is we're calling recursion on left and right to figure out whichever is the highest, we're going to take that number. But every time we go down on the levels, we need to keep track of how far did we go down, right? Are we doing that right now? I mean, are we adding anything to the number? +1, yes. So we can do +1 to the total here, and that would carry up the chain. So every time we go down, that we're going to do +1, +1. That's like we're going to keep going down and doing +1. Remember, every time you need a counter or something that you're going to add up, make sure you have a return and you're adding 1 to it. That's one way you can actually keep the counter. So we're calling recursion on the left side and the right side, and we're just taking the maximum of whichever one it is. We don't know if it's going to be left side or the right. Let's test it out. So we have car tree in order. We're going to take this out and I'm just going to print the car tree. And then I'm going to print car tree dot, and that prints 4. We have, let's count it. We have 1, 2, 3, 4. On this side, we have 1, 2, 3, 4 on the right side as well. So 4 is correct. That makes sense? All right, so let's go and write a different function. So the remove function is one of the hardest one to write. We're not going to do that in this class. Like I said, we're going to be working on it after once you get into bachelor's, like algorithm or data structures, because you need to rebalance the tree after you remove it. So what happens if you remove the middle one, the root itself, then you need to rebalance it. All right, so what else can we write? So if right now we have a size variable in there, right? So that keeps track of how many nodes we have. What if we didn't have anything like that and we need to calculate the size? How can we do that? So it would be very similar to the height function. So I'm going to copy the height function and we're going to try to modify this. So we have the height. Instead of that, I'm going to change that to size, not get size. The size, I know this is kind of redundant because we have the size variable. What if it didn't? I just want to do this for practice. And here I'm going to change the name of the functions to size. And this right here, I'm going to call the size function. And in here, I'm going to call the size function, not height, size function. And here I'm calling the size function. So what we're going to do, instead of taking the maximum of the left or the right, we're just going to add all those up. So what we're going to do is we're going to delete the max. And instead of a comma, we're just going to add everything up. So every time we come across a non-null node, we're adding 1 to the total. So we're calling recursion on the left side and the right side. And every time we see a node, we're adding 1 to the total. Remember, every time you add 1, you see a node, that's 1, that's 1, that's 1, 1, 1, 1, right? And what happens when you backtrack recursion? This 1 gets added here, and this 1 gets added here, so this becomes 3. And that 3 will come in here. Let's say if you don't have this. And 1 would get added here. This would become 3. 3 gets a return to the first recursion call. 3 plus 3. So this size would be 3. This would be 3. And you plus add 1 to it. So this would be 7. Right, let's write minimum, find minimum. How can we write get min function or find min function? So I'll get you guys started. So we're going to be public. And is it going to return a value? So it's going to be find minimum and it is going to return a value. But what value is it going to return? So in this case, let's do this is kind of messy now. So let's say we have a tree and we have a car object, car 1. Let's do car 10. And then we have car 5, and we have car 15, right? Something like this. I know that's not how they sort it, but we have something like this. Which one of these is the minimum? Which node? This node, this node, this node, this node, this node, which one? The far left, right? This is the minimum. So we need to write a function to get to this one. How can we do that? And what data type is it going to return? T, right? So it's going to return generic data type because that's what we're holding in the tree class. And we're going to say find min or get min. So use find min function. And what are we going to do in here? Tree is empty, so we're going to do if this dot root equals null, return null, and then we can do what happens here. Call recursion, yep. So we're going to call recursion. We're going to write the private method first, and it's going to be similar to the find min that we did above. It's going to be generic data type return. We're going to do find min, and the only difference is going to be we're passing in a copy of the root node. That's going to be correct. And how do we call the recursion here? Find min and this dot root, right? We're calling recursion. And if it's null, we're just going to stop. We're not going to be even going to call the second function. We just return it as a null, right? So remember, every time we have a return type here, make sure you're returning that from the main function, which is the public function. Otherwise, you won't be able to carry that up to change. All right. So now what happens inside the find minimum? If the current does not equals null, so once it gets here, that means we have at least one node, right, in the tree. So let's say once we get to the private line 116, we have at least one node. We could have more. We don't care about any of this, right? We don't care about any of these. We only care about going left from here, because we need to find the minimum. At line 116, if we know we have one node, we can check if this is null. That means this is the minimum already, right? So if the left node is null, that means this is the minimum. This could have a bunch of other nodes in here, but remember, we don't care about any of this. We only care about this side. So let's figure out the base case first, right? So the base case is, so if base left equals to null, right? So if that does equal to null, that means we're all the way at the end. Even if we're right here, how do we know this is the end? Let's say this is car one, because this equals to null, right? So we're going to check current dot left, which is this. If that equals to null, then we're at the one we need. So we can do return current dot data. Else, what are we going to do in the else part? So we're going to do return find min, and we're going to pass in current dot left. Doesn't matter how many, what's the height of the tree. We don't care how many times we need to go down. We'll keep going down on the left until we find a null node. As soon as we find the current, will be sitting here, and we're going to check the left pointer. If that equals to null, we're at the one we need. So we'll just print that current dot data. So it'll be the opposite, but instead of left, you'll go to the right. We can quickly change this. So let's copy all this, paste it, and we'll change everything to max, and this is going to be max. That's all the calls are to the max. And now instead of going left, we're going to go right. So every time we're mentioning left, we're going to go right. The base case is going to go right, check for the right as well. And this is the base case. Let's write equals method. So what equals method is going to do is going to check two trees if they're equals to each other. In order for that to work, we need to check, we have tree just like this, and we're going to have another tree just like this, right? So the data, let's add in the data. So we're going to have 5, 15. So I'm having integers right now just for simplicity, but we're going to use generics. So this is going to be 7, this is going to be 11, and that would be 17. So 10, 5, 1, 11, 17, and this is 15. So now what we're going to do is we're going to compare 10 to 10, 15 to 15, 5 to 5, and we're going to go through both of the trees to make sure each level is equal to the other tree. And if that is 17, this is 17, if this is 18, they're not equal. If it is something like this, they're not equal. Okay? So every single node, the data itself has to match the number of nodes, the where it is on the tree is going to match. So that's what we're going to write. So the name of the method, we can call it equals, and this is going to return Boolean. And what's the parameter? There's going to be equals method, return type is Boolean. What's the parameter for this? Generic tree, right? So this would be this tree, and this would be the other tree, right? So we need the other tree to compare to the one we have already. So this would be generic tree, and we'll call that other. For right now, just make sure you at least understand what we're trying to do, and we'll figure out what we need. So let's write the function. So it's going to be public, first one, and that returns Boolean, and name of the method is equals. That takes in another generic tree, and we'll call that, and that's going to be generic type, and call that other. We know we're going to call it recursion. There's no other well, there might be another way. The easiest way is to go down using recursion, and we're going to do same Boolean, and we're going to be equals method, and we're going to pass in other, in here. And what else do we need to pass in this? Or do we need to pass anything else? The node, current node, right? We still need the root. We still need to make a copy of the root. So remember, this is root pointing here. We're gonna make a copy of that. So in this right here, what we're gonna do is we're gonna keep it simple, and we're just gonna call recursion from that function. So whatever the other function is returning, we're gonna go and return it. So we're gonna pass in the other, and we're gonna do this dot root. So what happens in here? What could be the base case? So the current key is null. So if current equals null and other equals null. The base case would be is pointing to null, that's an empty tree, and other is pointing to a null. So there's nothing in there. We're comparing two null objects. If they're both equals to null, we can just say return true. In that case, that is. So we can use this as a base case, right? So if you're wondering why didn't we just use this in here before calling the recursion, we can move this up here, but we need this for the base case here as well. So if you put it in the first function and this one, that would be kind of redundant, right? So that's the other reason we didn't do it. On final, if you need to write a function and you have this case in both of the functions, that is fine. I'm not going to take off any points, but yeah, it's just for right now. I'll keep it simple. All right, what's next? Do we need another base case or just one base case is okay? If the current is different than, so what are we trying to compare now? We can test their size. Yep, that could be one of the base cases. If the size is not equal, then obviously they're not. Well, is there a case size? Yeah, we can have that in there. And before we even call recursion, we can have that case. We can add that in there. So we can do if other dot size does not equals to other current dot size. Instead of size, I'm going to do size function. Current is not letting me call that. Oh, we cannot actually do that here. Why cannot we do that here? Why can't we call size? Exactly. So remember, we're inside the tree class itself, and the only access we have is to the root. And the root itself is the node. We don't have access to the whole tree. So we don't have access to the whole class. We don't have access to size or any variables inside it. So we won't be able to do that. So you can probably find a workaround that. But the thing about it, so if current does not equal to null, and the other does not equal to null, then what's the next step we need to do? Check each element. So else if, how are we going to check each element? Other dot data. So we're going to pass in the node.
Yes.
And this would be the node also. Yes, this can kind of make sense. Before we're passing in the whole tree, but we don't need to pass in the whole tree. We need to pass in the root pointer of that tree. And we can access it like this. Yeah, that makes sense. All right, so now if we do other data that is available, and we need to compare that to what else? What do we need to compare this to? Current. What do we need to return? Return true. If they're equals, we're going to return true, right? But how are we going to go down the tree and make sure everything else is equals to the other tree? Call recursion, where are we going to call a recursion? What case? Or do we need another case? And the other thing is when you call a recursion, remember, when we're comparing this with this at that level, it's going to be either true or false, right? And we need to carry that true or false up the chain. And there's going to be a lot of true and false. And if one of them is false, the whole thing becomes false, right? So how are we going to incorporate that in there? Yeah. So what we can do is we can use this right here, and we can end the recursion with that. So whatever the recursion returns, we're going to end it with this. So we can modify this a little bit. So we can do if, or we can just take out the if. I guess it's going to be the else, and we're going to copy this. And instead of returning true, we're going to return the comparison of the two. We're going to return the data compared to the other data, and we're going to do recursion. And how are we going to call recursion? We know we're going to call the equals method. What are we passing in? On the left side, so it's going to be other dot left and current. Will it be right or left? Remember, we need to pass in two nodes, right, to be compared. Remember, if we're here, we're passing current dot left. We don't want to go like this. We want to go in the same direction. So other dot left and then current dot left.
Right.
So if we're going in this direction, we need to go the other direction as well. And then we need to end it and call recursion again. We're going to do other dot right and current. Is that it? Did we solve the problem? So right now we're still missing a case. What if this doesn't exist, right? So this is null, and here's 17. We don't have that case in there. So right now this would work if this is like a perfect scenario, and this is like 18, and this would return false, and then we're okay. What if one of them is null? So this is null. Remember, so here we only want to run this, right, when both of those two exist, like anywhere on the tree. I'm giving this example, but it could be anywhere in the tree. We only want to run this if these two exist. So can we add a check in there? Make sure both of them exist. How can we add a check? The OR operator, something like this. We copy this. And we need if, and so if remember, I don't think we need an OR, we need an AND. We need to make sure both of those two exist. If one of them exists and we try to run this statement, just the first part, we're trying to access the null data with the current data, that's not going to work. So both of these two have to exist. But in this case, we've got to make sure they're not null. If they're not null, that's the only time we're going to check. We're still complaining that we need a return statement, right? So both of these two return statements based off of a condition. What if these two conditions are not met? Like the ones, this is null. What should we do?
Return false.
Return false. So in here, what we can do is we can do else return false. So in theory, I think we kind of have two base cases. This one that returns true base case, and this would be the return false. Yes, maybe. Hopefully. Let's test it out. So what I'm going to do, I'm going to run this on the car tree. So I'm going to make a copy of this and change the name. So this would be car tree 2. I'll call that. And change the name to 2. Yeah, 2 trees. I'm going to print both of those trees out. I'm going to do S out car tree 2. And instead of printing it out, I'm going to do equals. So they're pass in car tree 2. And that would tell us true or false. So what should it return right now? True, right? Because I haven't actually changed anything. I'm just comparing both of those two. I'm going to run it and see what happens. So we have other dot data equals to current dot data. That makes sense. We are doing left and left, then right and right. The car object. Do we have any equals method? We don't. I think it's failing because we don't have an equals method in our car object. So it doesn't know what to compare in those objects. Let me test something. So we have a car object. What equals method are we using? So we're going to do car equals to new car. And I'm going to add, and this would be 15. And if we do car dot equals, so if you look at the equals method for the car, it's comparing equals to the generic, well, not generic, just the object itself, not the car itself. So it's failing on the equals method. So this solution works, I think. It's just the data that's stored inside has to have the equal method in there. Otherwise, it's not going to work. I'm going to test it out with this string one. We have a string tree as well. I'm going to make a copy of that and then test it out. If this works, then we'll come back and add an equals method to the car object. So string tree 2, 2, 2, 2, 2. And instead of printing car tree, I'm going to do string tree and print string tree 2. And instead of calling car tree, we're going to do string tree dot equals string tree dot tree 2 equals. All right, let's test this out. This should be true, and this one it is. Because remember, string, the first one we're only using string object, right? String object is coming from Java that has an equals method. We can actually look at that. So we can hold down the control, go into string class, and this has an equals method right here. So it's comparing each object. We need something like this for a car object for it to work. All right, so let's change something in here and see. We'll change this to, let's do, what else can we add? Object. We'll change one word to object, run it again, and now tree would be different, and we get false. Revert back the changes. So I'm going to add the same one I had before, and let's delete one of the last node that we're adding. So tree is not, everything else matches, but one side is missing this node right here. This side is missing that node and still false. So it's working. So now how can we get that to work for car object? We need to come in here and write a equals method. And that equals method is going to be, we can go and write it, since we only have two parameters, two fields, so we can compare both of those two. So we can do public, or you guys can tell me how are we going to write the equals method. So what is it going to return? Boolean, right? So we're going to return Boolean, and it's going to be equals. And what's the parameter? Car object, so it'll be other car. And what are we comparing? So in order for the object to be equals, we need to make sure all the fields are equal, right? Just like the tree has to be equal, all the nodes have to be equal. So in this one, we have two fields. We need to make sure both of them are equal, so we can do return this dot color dot equals to other dot color, right? And we need to make sure miles per gallon are equal. So we can do, so npg dot equals doesn't have that method because it's an integer primitive data type. So how can we add that in there? How can we check if the miles per gallon are equal? This dot mpg equals other. So it's going to compare all the fields. If they're equal, this whole object is equals, right? So now if you go in or testing, instead of testing this, let's test the car tree. I'm going to print it out first. And here, instead of string, I'm going to call string tree2. And let's see. So I haven't actually changed anything between these two trees, so it should be equals. So it should return true. And still getting false. But did I change anything? I didn't change anything. So let's test out this equals method first. Maybe we made a mistake here. Car1 equals to new car, and we're going to do black. And then let's do it. And I'm going to copy the same line, and we'll create car2 and keep everything the same. We're going to do car1 dot equals and car. We'll comment out this, and this. And we're going to surround that by system.out. So we're just testing out the car object equals method, and just to make sure what's going on. We need, for objects itself, we need to add a different class and extend it or implement it. But if you need to do that, I don't want to do that today. I just want to make sure why it's not working. It should be working. Yeah, so that's working. Let's try if it's false. I'm going to change this to 45. That's false. That's working. Change that to 50, and I'm going to misspell black here. Let's see if that's working. That is working. Yeah, I don't really see anything wrong with this. The equals method is working. But yeah, I don't really know what's wrong. I'll figure this out, why the car isn't working. But the function is correct. We tested the string. So let's see if there's anything else we can write. So it is 1016. So if I find something wrong with this and figure out what's wrong, I'll make an announcement and see what's going on. But right now, yeah, I don't really know what's going on. What about subtree? We'll count how many subtrees. Yeah, that one is a little advanced. Yeah, we need to figure out. Yeah. So let's do one more, and then scene right now. So yeah, let's do one more. I know you guys haven't had a break. Let's do one more, and then we can leave early. So let's do count internal nodes. It's a little easier than the equals method, hopefully. So we're not comparing two trees. We only have one, and we need to count internal nodes. How can we count internal nodes? What is internal node? So they're not a leaf, it's internal node. So how many internal nodes in this one? Two. Well, so this would be considered an internal node, right? So this would be this right here, 3. 3 internal nodes. And if we had something like this, how many internal nodes now? 4, right? So this wouldn't be an internal node because this has, this is not internal node. So this would be 4 internal nodes. So what's the pattern? How can you figure out what could be the base case? So let's go and start writing the function. So I'm gonna write it right below the equals method, and we're gonna do count internals, internal nodes, something like this. So it's gonna be public. What are we returning? Int count internals, or internal nodes, something like this. What's the, is there any parameter? Parameter, and for private, I'm gonna do the same thing, count internal nodes. And what's the parameter here? Node current. And we're actually gonna call recursion from this function to this function. But how are we gonna call the recursion? Do we need to check for anything? What do we need to check? If current, or then the private method. So yeah, so what about the public method? Do we need to check for anything, or can we just do return count internal nodes and pass in this dot root? What could be one of the base case in the recursion? Current equals null, we'll just return 0, right? Then else if, what else? So this could be one of the base case, or maybe the only base case. If current does not equal to null. Remember, so before we get into this, we need to figure out if it's internal node or not. How can we figure out if something is internal? Both of those two are null, or at least one of them is a null, right? So how can we check for that? Current, can we say that one more time? So we'll start to do a separate, does not equal to null. Current dot right is not equal to null. What should happen? So we can do return +1 and call recursion on left and right. Do count internal nodes, and that's going to be current dot left and plus count internal nodes current dot right. So we still need to return something, right? Both of these two are based off of condition. What should happen if they're not true? We need some kind of else. It's like the else if. So remember, if they are equals to null, what should we do? We need to stop the recursion, right? If we copy this right here, that's going to continue the recursion.
Yeah, just without 1 plus.
So you're saying something like this. If we call recursion and current dot left is null, that's the case. This is going to be right. So this is going to be the left is null and right is null. Left equals to null, or right equals to null. That's this case. One of them is null. But if you call recursion on null, then I think that would stop. That would get into the base case. So it should be okay. Yeah, I think that would work. Yeah, I had a different solution in mind, but I think this would work too. Let's test this out. So let's see, we have left does not equals to null and the right is null. Then we don't want to call recursion. So yeah, this should be and right here. Both of them have to be null. We need to check for both, and they both have to be yeah. So that, I think that should be end. Let's test it out and see if this is working. Where can we test it out? I'm gonna comment this out, this, and let's do on not the part 3. We'll do string. I'm gonna do string 3. I'll print it out, and then I'm gonna do string 3, right? Dot count internal nodes. And we're gonna print it out, and we'll see if that's making sense or not. So we have 1, 2. Yeah, we only have 2, so this doesn't count. This doesn't count because the left is missing. So yeah, that is making sense.